Kia ora, everyone. Welcome to another seminar of the External Relations Network Initiative Program of the Reserve Bank of New Zealand. Today's seminar title is Climate Change Attribution of Extreme Weather Events and Their Economic Impact. This is a joint work of Professor Ilan Noy from the Victoria University of Wellington and Rebecca Newman from the Reserve Bank of New Zealand. This is a research about combining extreme weather events with socioeconomic data to identify the economic costs of extreme weather events caused by climate change. The authors estimate that the climate change attributed extreme weather events have cost the world $2.9 trillion between 2000 to 2019. So I would like to thank to both of you for sharing your findings with us, and the floor is yours.
Hi, everyone. Kia ora. And thank you, Malcolm, for initiating this, and thank you, everyone, for attending. I see that there is some interest in climate change, which makes me happy. Climate change doesn't necessarily makes us happy, but at least there is some interest in the community about it. So thank you very much. I think you can see the slides. Yes. So when Meltem approached me, I thought, okay, I can do some presentation on attribution. But at the same time that she approached me, Rebecca just finished her paper on attribution. So we decided to give you two for the price of one. So basically, we're going to try to cover two papers in this 1 hour. Both of them use the same approach and the same methodology. So I think it's feasible. But what we're going to do is we're going to change presenters midway. So I would start by just laying out the framework a little bit. Rebecca will then talk about the global attribution work, and then time permitting, I will talk about Hurricane Harvey. The Hurricane Harvey stuff that I will hopefully have time to speak about is joint work with several people. Dave Frame, whom I think maybe a lot of you know, is a climate scientist, climate physicist from Victoria. Michael is from the Berkeley National Lab in California, and Chris and Ollie are from the UK, from Bath. Somehow I missed Kevin Smiley, who is also in the paper, and he's a sociologist from Louisiana State. Anyway, what do we want to talk about? Well, the basic premise is that climate change is shifting distributions of both temperature and rainfall, and that the big action when a distribution is being shifted is not necessarily in the change in the means, even though when we speak about climate change, we constantly talk about is the average temperature going to change by 1.5 degrees or 2 degrees or 2.5 degrees or 3 degrees. Actually, the main action is in the tails. So the tails are becoming, when the distribution is shifting, the tails are becoming a lot more frequent. I think for anyone who has worked with statistics, that seems to be an obvious observation, but the magnitude of the change in the frequency is quite large. And beyond that, we start to get the kinds of events that we have never experienced before, not in terms of our historical record, at least. So we start to get these, that's the little red triangle there. We have unusual events. And just last July, we had a heat wave in the west of the United States and Canada, where the scientists determined that kind of event would have never happened without climate change. So the term they use is virtually impossible without climate change. So that's these events that we don't have a record of before. Beyond that, that becomes even worse if the distribution is not only shifting, but it's also flattening. So we take our tails, and we know that at least for some kinds of metrics, for example, precipitation, it is also flattening. And then again, we have even more extreme events that we've never experienced before. Okay, so the basic argument here is when we want to look at the impact of climate change, we need to ask not how much would a 1 degree or a 1.5 degree or a 2 degree increase in the average, how much will that cost, but rather what is the cost of these additional extreme weather events that we are experiencing because of climate change. Okay, that brings us to climate attribution science, which is exactly that attempt to quantify the changing distribution in the tails, okay, the extreme events. Okay, now if you think of this is a graph for precipitation, we know from a lot of research, both observational research and also modeling, that in many places the distribution of, if we look at the very tail of the distribution for precipitation, it is shifting to the right. Okay, so we are getting more intense events with higher frequency. Now, we can look, and that's where, you know, think of an event, the kind of event. Let's talk about Hurricane Harvey, which is the one we study later on. So this big hurricane in 2017. You can think of that Hurricane Harvey either as, say, it's a one in a, I don't know, 200-year event that is becoming more frequent. So instead of a 1 in a 200-year event, it's now a 1 in a 100-year event or a 1 in a 50-year event. Or you can think of the same 1 in 200-year event is now becoming more intense. Okay, so a 1 in 200-year event is no longer what it used to be before in terms of precipitation, but it is becoming more intense in the sense that it's producing more precipitation, right? So these are two ways to think about the changing in the tail, the frequency approach and the intensity approach. Now, the attribution science, that's exactly the way they look at it. They look at an event that happened, and they're trying to estimate either that event, what its intensity would have been like without climate change, so it would have been less intense, or how likely it would have been without climate change, so it would have been less likely. And that's basically two ways that are, at least in theory, equivalent to thinking about this this event. And in what we're describing here, in the next, almost an hour, is exactly, we look at one study that uses the frequency approach in terms of attribution, and one study that looks at the intensity approach in terms of attribution. And I think here I'm passing over to Rebecca.
Yeah, sure. Thanks, Ilan. Cool. So as Ilan's mentioned, basically what we wanted to do in this paper was understand how we could use these insights from climate attribution to try and use a new methodology to retrospectively estimate the global cost of extreme weather, but the proportion for which climate change is responsible. So referring to Ilan's last slide, what we're going to do is use the frequency approach for this global estimation, and this is done through the fraction of attributable risk. So the fraction of attributable risk, or the FAR, is the likelihood of an event that is attributable to a specific causal factor. So the causal factor here being the anthropogenic greenhouse gas emissions. So we calculated the FAR, the FAR is calculated as 1 minus the probability of the specific event happening in what we call a natural world, where a natural world is basically a modeled climate that has no anthropogenic emissions, so no effect of human-induced activity. And then that's divided by the probability of a given event, the same given event, in a climate change world. So in a world where humans have altered the climate. So you can think of this basically as what we experience today. So the FAR, and just a basic example, if we had an event which without climate change would be a 1 in 50-year event, but today it's actually recognized as a 1 in 10-year event, then we could calculate the FAR to p 0.8, which basically we can interpret that as meaning 80% of the risk of that event occurring is because of anthropogenic climate change. Cool. If I can get you to flick over to the next slide, Ilan, thank you. So basically what we want to see is where's the economics in all this? Where's the economic question? So what we did is basically applied the approach that Elon and Dave and his other colleagues had used in their initial Harvey research, and make the connection that if climate change is responsible for X%, so say 80%, as we talked about in the last example, of some given event occurring, then basically the connection is that then we can say that anthropogenic forces are responsible for 80% of the cost of that event. So this kind of breeds this basic, really simple calculation of the FAR times the economic cost to estimate the attributed cost of a particular event. So climate attribution science was basically only first proposed in around about 2003. So it's only been in the last decade or even less that climate attribution studies have been conducted on like quite a notable number of events each year. So that means we don't have FAR data points for every extreme weather event or even that many compared to how many happen each year. So to create a global estimate, we had to make some assumptions about what the FAR would be for different types of events across the world. So this kind of led through to the data collection process. So there wasn't an existing database which collected together attribution studies and basically the findings from those studies so that they could be used. So this kind of made up a substantial part of the research, bringing this all together. So we started with over 250 climate attribution studies that looked at extreme weather across the world. And we needed to refine this list to figure out what studies within that could be useful for making a global estimate. So we had to rule out some studies. So some studies that got ruled out included studies that looked at annual or multi-annual weather trends or global trends in weather, because you can't explicitly match economic costs to those kind of more trend-based attribution studies. Other reasons a study may have been ruled out in this research was if it didn't use the FAR, so it might have used a different kind of metric, or maybe some metrics you can convert to a FAR, but some you can't. So ones that you can't, those had to be ruled out so we could get a consistent approach. Otherwise, some studies may have been inconclusive or showed no impact of climate change, which basically meant they weren't going to get any meaningful results for us. So from that refined list, we went through the literature and collected basically the data out of those attribution studies. Whoa. So what we needed to collect was the FAR measurements for each event, and then kind of the temporal. So then the next part of the puzzle was basically collecting the economic data. So for each of those events which we had a FAR, we wanted to collect what was the economic cost of that event. So the first kind of port of call for finding the economic data was the MDAT database. So this is a global disaster database, which has a lot of great information. So most of these studies, we could get data on the economic cost. From MDAT, what we were looking to collect was the number of deaths, which we could convert using the statistical value of life, or as well as the total damages from the event and how much of those damages were insured. So those were kind of what we were aiming to get. So if they didn't have it at MDAT, we'd look to alternative kind of sources of cost data. So that could be, there's another Disinventa database, which was quite useful, as well as government agency reports, or kind of as a last resort, maybe media. So we could collect that together. So then once we had all that, where we had both a FAR and an economic cost measurement, that's what we called our matched events. So they kind of matched across a temporal and geographical scale. Then we could say that these were matched events and they kind of form the basis of what was the master database that we used to estimate the global cost. So if I get you to flick along, Elon. Cool. So this is kind of a subsection of the database. So there's 179 events in the whole sort of master database. So this just shows you a few and what we were collecting. So if I just pull out an example, so you can see we've got a New Zealand event in there, so a flood in 2015, which was a flood in the lower North Island. So I believe it hit Wellington relatively hard, so some of you might remember it. But basically this was assessed kind of by climate scientists to have a FAR of 0.3. So basically means that flood, climate change was responsible for 30% of that flood. So then we collected the total cost estimates for each of those, and then the attributed estimates, which are the 3 columns on the right, which basically tell us that there were, for the New Zealand example, climate change was responsible for no deaths in this event, but it was responsible for almost $38 million in damages. Cool. So creating this kind of database is really useful for looking at the individual events and understanding the climate-related costs of those specific events. But just what's in that database doesn't tell us that much about the actual global economic impact of extreme weather because of kind of the paucity of data on the FAR measurement side. So what we had to do next was kind of make some assumptions about what we think the FAR might be across the world, so we could apply that to broader bases of economic data. So what you can see here is basically the average FAR for continental and event type breakdowns. So this basically just looks at each of the events that kind of match those categories within our 179 events in the master database and says what's the average FAR for each of those. So this is where I kind of first started looking to think about how I could basically apply kind of like an extrapolation to a broader data set of economic data. So what you can kind of see on here is that the variation in the continental variation in FARs differs quite a lot depending on the event type that you look at. So if we're looking at heat waves, the impact of climate change on the frequency of heat waves is relatively consistent globally from the data that we have anyway. So kind of sitting between about 0.65 and 0.81 for kind of the average results across those continents. But then if we look to something like a flood, we can't say the same about that. So there's a greater regional variation. So you've got, for example, in Africa, a decrease. Basically, this is a negative FAR, which is something we could kind of refer to as a fraction of attributable decreasing risk, which basically means that climate change is making the events that these attribution studies had occurred on actually is making those events less likely than they would have been in a world without anthropogenic forces. Whereas in all the other continents, floods are becoming more likely because of climate change on average. There's a bit of an issue here though. If you look to the kind of the numbers above the top of each line, you can see that this is just a count of how many observations we have in each of these breakdown categories. And you can see that for some of these, so for example, heat waves in Africa, we only have one attribution study that kind of matches that combination of event type and continent. So that creates a bit of a limitation. In other areas, we even have no data points. So storms, for example, in Africa, Europe, Oceania, we don't have any information on FARs in those areas. So we can't say much about that. So this is one of the limitations that we ended up with. So we had to kind of judge that, relying on one study in some of these breakdowns could lead to too much of an overdependence on or an over-reliance on one particular study, especially if it was a study that had been done a long time ago, considering that attribution science has become more developed in the last few years. It didn't seem like a reliable method, so we had to kind of think of an alternative. So if I get you to flick on to the next one.
I've got a question here.
Sure.
When you're using issued papers, like published papers, 250 of them, if I reconsider right, do you weight them with respect to how well they are published or how reliable they are?
No, we didn't weight them, but what I did do was for some kind of quite high impact events, there'd be multiple, especially ones that have happened in more recent years, there'd be multiple attribution studies done on that event. So if that was the case for some of these events, then we would basically used SJR sort of ranking of the journal that it was published in to kind of dictate which one we use, so that we're getting kind of the best for each event. But other than that, no, they weren't weighted. Cool. Yeah, so looking over to this slide, so as an alternative to using those regional breakdowns, just because of the over-reliance on one or none.
Rebecca, can I just add?
Yeah.
Yeah. So we didn't weigh the studies, but generally speaking, a lot of the studies were in this annual issue of the American Meteorological Society's, I think that's the right name, publication that they do. So this is the premier organ. It's sort of the equivalent to the American Economic Association for climate scientists, and they publish this annual issue for attribution studies. So I think most of the attribution studies that we use are coming from the annual issue on attribution that they publish. And in general, they're all coming from published work rather than some kind of working paper, because climate scientists don't have the tradition of posting working papers. Yeah.
Yeah, cool. Thanks, Ilan. Great. So if you look over to this one, we kind of had to basically, given that there was only one event or no events in some of the regional breakdowns, had to think of kind of a second best alternative. So ended up using for extrapolation the global average FAR for different event types. Ideally, we wouldn't want to have to rely on the global average, and would prefer to make an extrapolation based on a more local average FAR measurement, because that would be more reflective of kind of the uneven distribution of climatic systems and influence of climate change over the world. But we didn't have that option, so this was kind of deemed as like a best first attempt to basically prove that this is a method that you could use, and you could make more granular breakdowns if the data was available. So then we did the extrapolation by using the FAR times cost method that I referred to before across all the relevant events in the MDAT database, using that global average FAR. So you can see on the slide basically how many events existed in MDAT, and this is across the 2000 to 2019 time period. So we kind of dictated that time period by the availability of FAR studies, so kind of fit within that realm. So as you can see, a lot of storms and a lot of floods occurring, and a few other ones. So the heat waves and things like that. Some of this might not be that there wasn't more heat waves, but that they don't have as much economic cost data on heat waves, for example. So basically, then we could aggregate the climate change estimates across all these events, the climate change attribute estimates. So this included the statistical loss of life, the uninsured damages, and the insured losses, kind of so we could figure out what is basically an estimate of the total global impact of climate attributed extreme weather over the last 20 or so years. So what we found is that the annual average was $145 billion, so that's US dollars. And we could basically pull out where there's different, so if you look at here, you can see that it varies quite a bit between the years for what events are, for what years there's kind of big peaks. So the bit that I'd urge you to look at would be the darker orange bars that represents the climate attributed costs as opposed to just the full cost of extreme weather over that period. So where there's peaks here, so if you think about 2008, 2010, 2003, these were typically actually really high mortality events. So for example, 2008 there was driven by a cyclone in Myanmar, so Cyclone Nargis, which led to the climate attributed deaths were more than 80,000. So with a sort of statistical value of life applied to that, it really boosts up. And then 2003 would be the heat wave in Europe that I'm sure many of you are familiar with, which led to a lot of deaths. And then in 2010 there was a big drought in Somalia, as well as a Russian heat wave. So that kind of shows you some peaks and where they occurred. Where the peak in well, it doesn't look so much like a peak, but the peak in the highest damages was 2017, which kind of links to what Elon will be talking about in a moment with Hurricane Harvey. Cool.
Another question about the statistical statistics of the probabilities. Some of those probabilities have a dependent structure, like if you have a wildfire in summer, in winter, floods are, the probability of having floods are higher. Did you incorporate that kind of a dependency structure when you are calculating the probabilities?
So we didn't really have enough observations to be able to break down to that level in terms of the FARs and say this one was happening in summer, this one was happening in winter, and build that in. So basically so it's done in quite a simple way, especially just applying the average FAR. And the purpose of that is mostly to say, here's the information we have now. It's not enough. There's not enough data, especially on the climate science side. So here's a basic approach, here's a basic methodology. As we get more of these studies, how could we improve on this? And then get more kind of sophisticated and robust estimates. So no, we didn't, but it would be a good idea. So go forward. Thank you. Cool. If we flick over to the next slide. So something we want to basically compare this to how climate change has been measured by economists in the more recent times. So we compared this to integrated assessment models. So for those who aren't super familiar, an integrated assessment model in the climate space anyway, creates a model of the economy, creates a model of the climate, and then basically models the integration between those two. So the main integrated assessment model that we compared these results to was the DICE model, which was basically created by William Nordhaus, who I'm sure many of you are familiar with, Nobel Prize winner. So the damage function that you can see at the bottom of this slide tells you how Nordhaus estimated the cost of climate change as a proportion of GDP. So basically, what all it is a damage multiplier of 0.00236 multiplied by the change, so a polynomial of the change in average mean temperature above a pre-industrial baseline. So this kind of calls to what Elon was referring to before, where these estimates are generally based off kind of a change in the average temperature rather than looking at how we have a change in the distribution of those tail end temperatures and what's happening at that end. So this is an example of that. So then if we go over to the next slide. Cool, so this has some of the results basically compared to DICE. So as I talked about before, our result was 145 billion annual average and costs from climate attributed extreme weather. The DICE model applied over the same time period, so 2000 to 2019, was estimated to have 138 billion annual average cost. But what I would urge you to think about is that this DICE model is basically trying to estimate the cost of climate change broadly. So rather than looking only at extreme weather, it's looking at the whole cost of climate change over that period. So it's a slightly different in that way, and generally you would expect that that would mean that this would be a lot bigger, but it's actually smaller. So Nordhaus recognized, I guess, that his model wasn't fit for necessarily estimating the cost of extreme weather. So what he did in this 2016 version of the DICE model is added 25% to the multiplier, and that basically was meant to account for the costs of extreme weather, but not only extreme weather, it was meant to account for the costs of other factors such as biodiversity loss and ocean acidification. And the allowance that was given for that in this figure over 2020 to 2019 is this $550 million per year. So a whole height smaller than the method we've got from the attribution study. So this basically should show you that perhaps he wasn't adjusting enough, but also the paper is meant to give another alternative way to measure the costs of extreme weather and then be able to build that into how we understand what the costs of climate are from an economic perspective. Question from Adam, I see about the net costs. Yes, these are net costs from the attribution study. So where there was negative, when the cold events which had negative global average FARs, those costs were taken away. Cool. I will hand back to Ilan to finish off on his part.
Thank you, Rebecca. That was great. So what I want to use maybe 15 minutes and then we can have time for questions is to talk a little bit about Hurricane Harvey, because if you remember way long ago when I started speaking, we talked about two approaches. One is the intensity approach and one is the frequency approach to do attribution science. And here we're using the intensity approach, while Rebecca was using the frequency approach. So Hurricane Harvey, if you remember, was a very tough hurricane. But what was unique about it was tremendously wet, and the then resident of the White House said that it was the wettest we've ever seen from the standpoint of water. Pretty accurate description. We don't think that there was any other liquid involved, but this was what was unique about Hurricane Harvey. It was not a particularly strong hurricane. At the time it hit Houston, it was a category 3 out of the, up to, this can go up to category 5, but it dropped a hell lot of rain because it moved very, very slowly. It was also the second costliest hurricane in US history, actually in world history. So it's a worthwhile event to study. Now, it's important for us that the main issue with this hurricane was the rain and not the wind, because it's very difficult to model how much wind the hurricane is producing, but it's much easier to model how much rain it is producing. And how much rain it is producing is basically a function of two parameters: how much moisture it's gathering from the ocean when it passes the ocean, and how fast it is moving. Now, both of these things were affected by climate change because the ocean around Texas at the time was much warmer than usual at that time of year. And hurricanes are moving more slowly when an ocean is warmer. So both of these things are connected to climate change. Okay, that observation was not lost on the climate scientists. So they produced these both intensity and frequency studies of Hurricane Harvey. And what we're focusing in this case is on an intensity approach, which basically tries to say how much of the rain that Hurricane Harvey dropped on the city of Houston was because of climate change. Now, the estimates here vary a bit. There are several papers that have looked into that. But at the lowest bound, they say that 7% of the rain that fell was because of climate change. And at the upper bound, it's around 50%. What I'm going to show you here is 38%. We argue in a paper that we are hopefully soon publishing that 38% is probably the most reliable number. But of course, one of the authors on our paper is one of the authors of the 38% paper, so you can take this with a bit of grain of salt. But in any case, we produce in the paper the various range of scenarios from 7% all the way up. So you can see that qualitatively the results don't really change. The magnitudes do change a bit. Okay, so what we do is on that observation that say 38% of the rain was because of climate change, we can do with hydrological modeling, we can map for the city of Houston. We know how much it flooded, and that's the upper left map. But we can also take down 7% of that rain and model where would have been flooded if there was 7% less rain, or 38%, which is our preferred estimate. So that's the bottom left panel. That's how much rain there would have, how much flooding there would have been with 38% less rain than actually happened. Now, if you want me to, I can't provide more information about these maps. I'm colorblind, so I have no idea what they show. But presumably what they show is that the bottom left has less flooding than the upper left. Okay, and that's our argument. Without climate change, there would have been less flooding. Okay, so what we can do then, now mind you, the granularity of this mapping is very, very detailed. So that actually means that we know for each building in the city, for the 1.1 million buildings in residential houses in the city, for the 1.1 million residential houses in the city, we know how much it flooded, and we know how much it would have flooded if there was no climate change, okay? No anthropogenic greenhouse gases, okay? So for example, 10 Main Street flooded by 1 meter during the hurricane, but without climate change, it would only have flooded by, I don't know, half a meter or something like that for each building, because the topography is different, and because of the hydrological modeling, it doesn't necessarily mean that it would have flooded 38% less. It possibly means that it wouldn't have flooded at all without climate change. Right? That's why we need the hydrological modeling. So then we have once we know that for every building in the city, we can match that with other sources of data on these buildings. So we use basically the value of each one of those. This is the appraised value for tax purposes. So we have the value of each building. We have what kind of building it is. That's the data on buildings from the National Structure Inventory. So basically, they categorize all of these buildings into 38 types, and they tell you, this is a 2-story wooden frame single home, or this is a 3-story, three apartments building, or whatever it is, made of bricks, and so forth. And then we also have damage curves from the same source. So these same source produce damage curves for flooding. So that means that for a single-story wooden frame home, the damage from 50 centimeters of flooding is, say, 20% of the value of the home. But from 1 meter, it's 40%, and from 2 meters, it's 100% of the value of the home. So the home is a total loss. So we have these damage curves for all of these 38 buildings. That means that for every building in the city, we can say how much damage it incurred, roughly, and then how much damage it would have incurred if there was no climate change. Okay, so that means we can identify the damage, the attributable damage to climate change for each one of those buildings. So John Smith, who lives in 10 Main Street, would know that their house had $100,000 of damage. 30,000 of that is because of climate change. Okay. Okay, and then we also have data from the American Community Survey about we don't have that on the individual buildings, but from census tracts. So this is sort of the equivalent to the mesh blocks in New Zealand. So we have some kind of information about the ethnic composition of the neighborhood, the average income in the neighborhood, and things like that. And then we have the FEMA flood maps. The FEMA flood maps are basically sort of similar to what local councils in New Zealand make, and that describe where is the 1 in 100 year flood zone. That is not necessarily important or accurate. Actually, most of the properties that flooded in Hurricane Harvey were outside the flood zone. But the reason it is important for us is because if your house is in the FEMA flood zone, you need to purchase flood insurance. If you have a federally owned mortgage, which most houses do. So if you are outside the flood zone, you don't have to purchase flood insurance. If you are inside the flood zone, you do. So for us, this is a proxy for having insurance, because we know that most people who don't have to purchase flood insurance don't. Okay, so what do we find? Here you can think of those buildings. So overall, from the 1.1 million buildings, about 100,000 buildings, just a little bit more than 100,000 buildings flooded. Now, of those, we can calculate how much of those that had flooded would not have flooded if there was no climate change. So if you think of the 38 scenario, which is our preferable scenario, that's the right column there, half the buildings would not have flooded if there was no climate change. So of the 105, about 50,000 would not have flooded if there was no climate change. When we look at the damages, the share is a bit different. So here, the climate change induced damages is about almost 60% of the overall damage. So about 2.7 billion would have occurred anyway, and 3.7 billion is because of climate change. Okay, that's different. That difference, it's not 50% but 60%. That's because every building has some kind of climate change damages associated. Every building that flooded has some kind of climate change associated damages with it. Okay, so what can we say? So we can just, this is just descriptive statistics of the properties in the city. About a third of the property, just a bit more than a third of the city is Latinx, which is the current way to say Hispanic. Let's stick with Hispanic because it's easier. So if you look at the share of Hispanic-owned properties in each one of those groups, so these are the uninsured outside the flood zone and the insured inside the flood zone, and we can think of three types of buildings. A buildings, these are the ones that didn't flood. B buildings are the ones that without climate change, they wouldn't have flooded, but they did flood because of climate change. And the C buildings are the ones that would have anyway got flooded, but they became more flooded because of climate change. Okay, so if we look at the ethnic breakdown there, you see that inside the flood zone, so those that are insured, it's roughly constant. So the Hispanics are roughly 40% of the buildings in those three groups. But outside the flood zone, the Hispanic share is much larger for these B and C groups. So these are the properties that were flooded and that were flooded because of climate change. So already that sort of descriptive statistic gives you a sense that there's something with Hispanic-owned buildings that seems to sort of bias, in a sense, them for getting more climate change related damages. We can then basically do regressions. So we have about 1.1 million observations. We can look at the depth. So this is the attributable depth of flooding for each building in the city. So how much additional flooding that building got because of climate change, or we can look at the attributable damages. So how much additional damage that building got because of climate change, and then we can try and associate that with these various other metrics that we collected. So for example, is it a multifamily home? Yeah, well, multifamily homes are negatively related to that. So multifamily homes are less likely to get more climate change attributable damages or flooding. Okay, appraised value is positively correlated, but there is a convexity there because once you square it, you get a negative. If it's inside the flood zone, the FEMA flood zone, then they're more likely to get flooded because of climate change. That's not terribly surprising. But the important thing for us is that if the higher the proportion of Hispanics in that neighborhood, the more likely they are to experience attributable depth of flooding and attributable damages. And when we interact at so median income, I should say, is positively correlated. So the higher the income in the neighborhood, the more likely they are to experience damages from climate change in this event in Hurricane Harvey. Not terribly surprising and we see that in a lot of places because there's much higher value and higher income neighborhoods along the coasts and along areas that are more sort of have better amenities because they're next to water bodies. But then when we interact median income with the ethnic composition of the neighborhoods, it's only for the Latin population, for the Hispanic population, that we get a negative coefficient, meaning that relationship between income and the damage, the attributable damage, is reversed for the Latinx, for the Hispanic population. Okay, so what are the key findings of this work? Neighborhoods with more Hispanic residents had more climate change attributed flooding. Neighborhoods with higher incomes had more climate change attributed flooding. But it is the low income Hispanic neighborhoods that had more climate change attributed flooding. So for that relationship is reversed for Hispanic neighborhoods. And then this is even worse for, and this is, I didn't show you in the regression, but we have another set of regressions that shows that. That's especially true for if those are Hispanic neighborhoods that are uninsured, meaning they're outside the FEMA flood zone. Okay, so it's the low-income uninsured Hispanic neighborhoods that get disproportionately hit by this event, by the climate change part of this this event. Now, one last slide, and then maybe we have a few minutes for questions. Why do we care about all these calculations, both what Rebecca showed you and what I showed you? You know, one argument is, well, if you're still dealing with people who don't believe in climate change, that kind of, you know, if you tell John Smith that his house had $30,000 worth of damages because of climate change, that might convince him that climate change is real. And of course, there's a lot of these kinds of John Smiths in Texas. But more generally, we know there is quite a lot of research on that extreme weather events convince people that climate change is real, especially the kinds of extreme weathers they haven't seen before. But here we are actually, but actually this is not the case because extreme weather events are not a proof that climate change is real. What we are focusing here is on the actual part of these extreme weather events that is related to climate change. So we're giving more structure to that argument. You know, the second potential use for this is in lawsuits. There's an increasing number of lawsuits, especially in the US. Those kind of lawsuits haven't yet used much of this kind of calculations that we've presented to you today, but there's many ways in which they can. So John Smith now has $30,000 of damages that he incurred for his house that he can blame on climate change, and therefore potentially can sue, you know, potentially the government or potentially, I don't know, the main oil companies for those, the liability to those damages. So there are these other uses for this besides the one that Rebecca suggested, which is, you know, once you look at those numbers, you realize that the integrated assessment models are currently underestimating the current cost of climate change. And if they're underestimating the current cost, it is very likely that they are also underestimating the future cost of climate change. I'm going to end there and leave time for questions.
Thank you. There are 3 questions in the chat box, and Nivan asks, have you accounted for the possibility of double counting damages from extreme events and the general rise in temperature?
I think I need more detail about what do you mean by double counting.
Like, for example, he says a hurricane might destroy a coastal city that would otherwise be lost to the sea level rise from the rise in the average temperature. Are these damages counted twice or somehow appropriated to extreme events and general climate change?
So we haven't calculated anything around sea level rise, for example. So that's one of those things that Rebecca said. William Nordhaus potentially includes in his estimate. Our estimate doesn't include those things, so we can't double count them. We're not, they're just not part of our calculation. We're only looking at extreme weather events. Yes, there are a lot of other impacts of climate change, and potentially you can think there might be some double counting once you start add them up. We haven't added them up, so that's not an issue for what we're doing. Or maybe I misunderstood the question.
There is another question from Daniel Wills. Net costs, can the DICE model account for change in distribution of production over time due to climate change? For example, some colder regions becoming more productive for agricultural production, providing some offset to costs damages in other.
The DICE model is one of a set of integrated assessment models. The DICE model is a fairly, in spite of the one that it's sort of won William Nordhaus the Nobel Prize, it's one of the simpler ones. So there isn't that much breakdown, sectoral breakdown, and so forth. There are other integrated assessment models that have more nuanced economic modeling, but sort of universally, they all produce numbers that are much lower than ours. We compare this to DICE because DICE is the famous one, the one that had a Nobel attached to it. But the answer is some of the integrated assessment models do account for all of these things. Yes.
Is the FAR number the same at the start of a decade as at the end?
Is the what?
Sorry.
Are the FAR numbers constant?
The same at the start of a decade as at the end? So is it time varying?
The FAR is calculated for a specific event that happened for that period, for that specific time. So when they calculated for Hurricane Harvey, it was both an intensity calculation and a frequency calculation. That took under considerations the amount of greenhouse gases in the atmosphere in 2017. So if that event had happened in 2012, there would have been slightly less greenhouse gases in the atmosphere. Not a big deal because these are cumulative rather than annually determined. But if the event happened in 2012 and that we have events in the data set that Rebecca has reported on from 2012, then it would have taken the amount of greenhouse gases in 2012. But if the question is, will over time those FARs change? Yes, they will change. They're becoming bigger for most types of events. Again, Rebecca showed for cold waves, they're becoming, these events are becoming less and less likely. In some cases, those events are becoming sort of -1, meaning impossible. Right? So some cold events in some places will become impossible with climate change. I think that answered the question.
So there is another question from Jack Bisset. Do you think New Zealand is in a good position to do work that leverages your research given no NZ IMAs?
So the initial impetus for this work, matching attribution and costs, was a Treasury report that Dave Frame led back in maybe 4 or 5 years ago. in which we calculated the attributable cost of in New Zealand in the past 15 years or so. That's a Treasury report in a published paper that you can find. You can find it on my website. But I think there is also an opportunity to do the kind of work that we've done with Hurricane Harvey, to do it within the New Zealand context, to examine exactly, what kind of populations are